everyone, this is Dr. Anna, and we are in physical geology right now. And the next topic we're going to talk about is the structure. So let's jump in. When we're talking about strain or deformation, we know that that is caused by stress, not just with us, when we don't look exactly the same as we used to look. Most of that deformation also happens because of strain, which caused by stress. So this is how it looks like when it acts on humans, and this is when it acts on rocks, which is funny. We have three kind of stress, and this is important to know because I might ask it on the final. The first one is compressional. When you play this slideshow, actually it shows you that when we have compressional stress, the forces acting toward each other, like, it's a bad example, but like when you have a car wreck or somebody has a car wreck, I hope it's not going to be you. When you have a car wreck, and let's say it's like a frontal, then what happens? The forces acting toward each other, I have to turn it this way. So acting toward each other, the two car gets together and they go into each other, and the result is always going to be relative shortening because they kind of going to wrinkle out. So the force is acting toward each other, and the result is relative shortening. Now, what kind of plate boundary would you see this? Yes, most likely convergent plate boundary. So you will see this at convergent plate boundary. Convergent. And the end result is shortening. Shortening. My writing is not so good today, but we are talking about shortening. So the end result is relative shortening, and you will be able to see it pretty good when you play this slideshow. The second kind of stress is the so-called tensional. When we're talking about tensional, that means that we are pulling things apart. So you have to imagine, I have to go this way, it's exactly the opposite. So you have to imagine that you have to leave someone and you're trying to hold on to each other, like hold on to each other as long as you can. So you can almost see that when you have forces acting away from each other in opposite direction, then you're going to have relative lengthening, which I actually said right here. And what kind of plate boundary will it be? Obvious. Yes, you're right. It's going to happen at divergent plate boundary. That's where the continents are pulling apart, divergent. Here we are. And then the third kind of stress is the so-called shear stress. When you got shear stress, the forces are acting against each other, but also next to, and it will result in displacement. You will not have relative shortening nor lengthening. The rocks are going to displace next to each other. So that's the shear stress. So altogether, the three types of stress is the convergent, the relative shorten with the relative shortening, the tensional. The first one was compressional. So compressional, tensional when you are having things pulling apart, and the shear when they are just sliding next to each other. So those are the three together. Now the next topic we have to talk about what kind of strains we can see. The strain is the permanent deformation. The strain is also called deformation. I shouldn't say permanent because we are right here. The first one is, which is what we call elastic. When the strain is elastic, you're playing with a tennis ball basically. I actually just found a really cool squeeze ball. So when you have a squeeze ball and I'm acting all the force I can possibly put on it, and you can see that it really changed the original shape. So we have strain on it, but as soon as I let this ball go, look, it goes back to the original shape. So I squeeze it, you can see I changed the shape and everything, but when I let it go, it goes back to exactly the same shape as it was originally. This is what we call elastic strain. Now, if you have rocks which are strained beyond their elastic limit, that's when you're gonna have permanent deformation. In this case, they cannot possibly recover their original. In this case, we have two cases. One is the so-called plastic, when the damage, the permanent changes is like folding or something like this. That just means that if you pick up a piece of rock, there is just no way that you could bend it. So there is no folding when it's colder. So to be able to actually fold something, you have to have high temperature rocks when the temperature is high enough that these rocks actually become ductile or completely foldable. Ductile is the word for it. So basically they will fold like this. You can see it's a really complicated fold. So this only happens when the temperature is high. Where would you have areas where the temperature is high? You're right, along convergent plate boundary, one plate is going under and the other stays up. So as it goes under, the deeper it gets, the higher the temperature. So therefore the rocks are more and more ductile, plastic if you wish. So therefore they will be able to fold. On the other hand, when the temperature is cold, so I mean close to the surface, the rocks are usually very rigid. They won't be able to fold. It's not plastic or ductile. So they are rigid, which means that they will actually fracture. They will break. Like you can see fault line here, fault line here. So in this case, the rocks will break. So the type of strain will depend on a couple of things. One is the kind of stress. What kind of stress happen here? Like, is it like one big huge stress which you cannot stand up to, or the amount of pressure is a whole lot at one time, or it's a small gradual pressure, or is the temperature really high or very, very low? What kind of rock? It depends. If it's a granite, it can stand much more pressure before it strains permanently. Or if it's a shale, most likely it won't be able to stand so much pressure. And of course, how long has this pressure been acting on the rock? That also is very important. So all these things are kind of important to understand what kind of deformation you see on the rocks at what time. So these are very important things. And now we can actually turn to the place where we will be able to tell what kind of deformation happened. For telling what kind of deformation happened, we have to be able to see and actually represent the rocks in 3 dimensions. Most of the time when there is permanent deformation or permanent strain, the rocks will not be horizontal anymore as they originally were. So we have a rock layer which is bent or tilt, and you want to be able to show it in 3D. So the way we do it in geology is that we represent that plane or the rock layer with the help of 2 lines. One line is the so-called strike, and the other one is the so-called dip. The strike is the line actually which is formed by the intersection of the rock layer, which is right here, and an imaginary horizontal plane. So the way geologists do it, that they use a so-called compass. They put the compass to the rock, and there will be a line formed at the intersection of the rock layer and the horizontal plane. And then with the compass, they measure the direction of this intersection. So remember the intersection of the rock layer with the horizontal plane, and that is going to give you the strike, and then you measure the direction of the strike with the compass relative to the north. So that's going to be the strike. Okay, so I think I have right here. So the strike is the direction of the line formed by the intersection of the horizontal plane, right here, with the tilted rock layer. And the orientation of the strike line is defined by a compass, which that direction measured relative to the north. And the other line we're using is the so-called dip. A dip is the measure of the maximum angular deviation of an inclined plane from the horizontal. So basically here is our inclined plane, and the angle is going to be measured between the inclined plane and the horizontal plane. So that's the maximum angular deviation of your rock layer from the horizontal plane. And you have to measure it perpendicular to the strike, because that is the only way you can get the maximum angular deviation. Okay, so we always have to make sure that we're measuring the angle of the dip in the dip direction, which is always perpendicular to the strike. Before I go on, so therefore, if you have a map, a geology map, which has all the rock information also, a geologist usually will show the strike and the dip just like that on the map. And so this is going to be the strike relative to north. So you know, if this here is north, north is usually straight up, so this means to be straight up. So therefore this here is like 110 degree or so right here. So it's 120 east. And this here is the direction of the dip. And usually you put an angle right here. And that is going to tell you the angle of the dip, which is the maximum angular deviation from the horizontal plane. So you know that this rock is going to be tilted right here by 30 degree. And when you see that on the map, you will always be able to imagine this rock in 3 dimensions. So definitely a geologic map is always better than a topographic map, because on the geology map you can tell what kind of rocks, what age they are, and how do they look in 3D. So let's start with folds as the structural element. The folds are plastically strained, so it's very important that folding only happens deep down in the earth crust, where the temperature is high enough that the rocks are ductile, so they will be able to fold. So these are typical folded layers right here, as you can see. Now, what kind of folds do we have? These are going to be the type of folds, and you should know it because I will ask you to please draw and sketch and list the different types of folds. So the first one is the so-called monocline. When you have a monocline, that's just a simple band, as you can see right here. And actually, when you play this slideshow, it will act. It's an animated picture, so it's going to play, so you will understand it even better. The next one is the so-called anticline or up-arching fold. And right here, you can see the strike and dip directions. If you look at a geology map, it's going to make it really easy, because you got the first of all, the anticline always have an axis right here. That's the axis, like right here. That's the axis. And this here, right here, is a so-called symmetrical anticline. Symmetrical anticline just means that this area, this plane here, basically divides the anticline into 2 absolutely symmetrical places. So that's the axis. And this here is the limb. Now, if you try to fold it back, you can see that the original layers right here were like that. So, you can tell that the oldest layer is in the middle. So that's the oldest, 1, 2, 3, and then 4, So the oldest layer is going to be in the middle of the anticline. And if you look at the map view of an anticline, and this is like all the layers of an anticline, you can see that when you have an anticline, the strike and the dip is going to go opposite. So the dips are going away from the axis in terms of anticline. And of course, when you play this slideshow, this is going to move. Now this one is just showing you the so-called regular, normal, symmetrical anticline, like up here. And this is the so-called plunging. When you have plunging anticline, that just means that the axial plane actually has an angle with the horizontal. So that's plunging anticline. So this is just normal regular anticline. This is the so-called plunging anticline. As you can see, the valley and ridges are nothing but synclines and anticlines, and the syncline is coming up. So right now, right yet, you only know about anticline, but the opposite is the so-called syncline. So it takes us to the syncline right here. So when you have syncline, it's the opposite of the anticline, and you have the so-called down arching fall, like right here. Okay, I'm gonna stop right here. This is the end of the first segment, and I will show you the second segment in just 1 second, okay? So just stay tuned. Bye.